Okay, all yours.
Yes. Hello, everyone. I'm Rebecca Hicks. I'm a graduate student at the University of Pennsylvania, and I'll be talking about my recent project with my advisor on falsifying string theory at a collider. And there's a paper on arXiv now with the same name. So what's the motivation for this project? So in general, it's difficult to make verifiable claims about string theory. The string scale is too high energy to probe directly, and there's a vast number of low energy vacua. So we instead want to ask, is there an experimental signature which we cannot construct in string theory? And what would it mean if we saw that? So to make that idea a little more precise, we make the following conjecture. That is, it is not possible to construct a low energy solution that is both a high dimension representation of the standard model gauge group and that appears in isolation. Um, so what would happen if an experiment detects a high dimensional representation of the standard model gauge group in isolation? And specifically, I'll try to focus on trying to realize the five-dimensional representation of SU2. So to motivate the conjecture a bit, I'll mention ways to realize matter in string theory. So first, we could consider the modes of an open string. Each end can carry a Chan-Paton factor, and allowing for orientation reversal, we can attain classical Lie algebras. However, in general, or for open strings, we only have two endpoints, so we can at most have two index representations of a single gauge group. So if we want a high dimensional representation, such as the 4 index of SU2, we can't attain it this way. So we could consider doing something else. What if we had a string bound state? So in type 2B string theory, we can form strongly coupled bound states of open strings, and this essentially allows us to work with more endpoints. So in this situation, we could consider starting with, let's say, the adjoint representation of E8, and then we could consider this breaking down into the standard model gauge group representations plus something extra. But because we require the standard model gauge group, this restricts the breaking patterns we can realize. So if we consider decomposing E8 into this standard gut breaking pattern, you can see this 248 dimension representation decomposes in this way, and this is known to reach the standard model gauge group representations, but it doesn't allow for these extra things, such as this 5-dimension representation of SU2. So perhaps we could do something else again. We could look at closed strings, and we could consider 2D CFT with something more like a more exotic current algebra. So let's say we have one with a global SU2 symmetry. So we have a current algebra at some level K. We know that the contributions of the sector to the conformal charge is 3K over K plus 2, and this will be less than or equal to 3. And the primary operator weights they need to be less than or equal to 1 for us to have the massless spectrum. And this weight is generally equal to J times J plus 1 over K plus 2. So perhaps we could try taking K to infinity and J to infinity, or just making them very large. But this still poses a problem for our conjecture because we want this 5-dimensional representation in isolation. So then this question becomes, what do we do with primary operators of lower weight? You could perhaps consider trying to construct some kind of projection to remove these operators, but it doesn't seem clear that you could do this without rooting modular invariance. You keep trying to pluck out low energy primary operators. So this also doesn't seem very reasonable. So with those examples in mind, there are certain high dimensional representation scenarios that we already care about. In particular, they exist in certain minimal dark matter models. So for example, this paper from Sorelli, Bernengo, and Strumia introduced a single Majorana field in a 5-dimensional representation of SU2. They tend to require this particle to have a mass of about 14 TeV to explain the thermal dark matter relic abundance. But the point here is that there's already experimental programs aimed towards searching for this particle for dark matter. However, you don't need this to be a dark matter particle. You could just have it as an addition to the standard model. And so we'll consider this addition of a single Majorana field and arbitrary n-dimensional representation of SU2. And we'll look at how this would show up in colliders. So to talk a bit more about the specific model we're considering. So again, we're just adding this single Majorana field. We're picking this model to be neutral under the U1 hypercharge. So there's no anomalies. This is just for reasons of simplicity. This also forces the charge assignments of the multiplet. So for example, if n is 5, we always have this neutral state, a state with a single charge and a state with 2 charge. There's also restrictions we can place on n. So because we're adding this fermion to the standard model, this is going to affect the values, or this is going to affect the running of the SU2 coupling. And the main point here is that if you keep pushing up the representation, this running of this coupling is going to accelerate and you're going to run into a perturbativity bound. So for that reason, we're only going to consider n being 5, 7, or 9. One other important thing about this model is that radiative corrections lead to a mass splitting between these charge states. It works out that the predominant contribution is from the diagram from a photon. And so you get this proportionality of q squared minus q prime squared times about 166 MeV. One main thing to note here is that this is a pretty small mass spectrum. And so what it does is it leads to a relatively short lifetime between these states. So if we want to look at this signal at the LHC, what would we have? So for example, we'll have a proton-proton collision. The constituent quarks can exchange photon Z, and we might get a pair production of some like chi plus and chi minus, or chi plus plus, chi minus minus. Or we can have a W boson exchange, and then we could have chi plus, chi zero, chi plus plus, chi minus, things of that nature. We can also have some initial state radiation, or this is usually called a jet, I guess, experimentalist papers. But some emission of gluons or quarks that hadronize. And as mentioned, the produced chis decay down to this chi-neutral state. For the most part, it's emitting soft pions, but the main point is that these pions are really too soft to do anything with in the detector. And this charge, or this state with a single charge, chi plus, chi minus, it has a mean lifetime of 44 centimeters over n squared minus 1. But the point of this is that it's long enough for some of these chi plus minuses to traverse part of the detector, and so potentially you could do something with it. To give a number for a specific representation for n equals 5, this is about 1.88 centimeters in terms of like a length. So to outline a search strategy, I'll mention some more specifics of the Atlas detector. So imagine looking down the beamline. the main pieces to point out here is there's one piece that's deals with tracking. There's an electronic or electromagnetic calorimeter, measures the energy of primarily electrons, photons. A hadronic calorimeter measures the energy of hadrons, and a muon spectrometer. So at the tracking part of this detector is composed of 3 subdetectors, and the very most inner detector here is the pixel detector. This starts at about 3 centimeters out and ends at about 12.25 centimeters out in a radii from the beam point. So we want our, let's say, chi plus to go all the way through this pixel detector. And if it decays, then that's fine. Our neutral state goes through and we don't see it. And this soft pion essentially loops around and we can't do much with that. But the hope here is that the tail end of events make it through this pixel detector. If you calculate the cross-section and assume a luminosity of, let's say, 140 inverse femtobarns, and you consider this mean lifetime, you still have about order 10 events making it through at a tree level mass of 600 GeV. And so it's hopeful that you could actually see this. So to summarize this general strategy, we essentially have 2 objects to work with. We have some jet and a disappearing track. This disappearing track is not part of standard reconstruction, and so we need something else to trigger on. We know that we have momentum conservation in the transverse direction, so if we see the jet, we can know that there's some missing momentum in the transverse direction. And to mention what the trigger means, so at the LHC, there's about 1 billion proton-proton collisions per second, so you can't save all of that data. You need to select important events to analyze. So one thing we can do is we can trigger on the missing transverse momentum, and then we can try to analyze the event to isolate our signal disappearing track from background. So one thing then we want to ask is there some existing collider search with a similar search strategy that covers this? And indeed there is. So there are long-lived Chargino searches at Atlas. They're also at CMS, but just focusing on Atlas for simplicity. So they consider signal events with practically identical signal event structure. And so what we want to do then is utilize the search to derive current limits for our NPLET model, and then we'll project these limits out to the high luminosity LHC upgrade. So I'll summarize the cuts used in the Atlas paper. So of course they require there to be at least 1 disappearing track. They don't want any electrons or muons in the event. If there's some kind of W boson resonance, you'll produce neutrinos, which can be a source of missing energy, and we don't want that. You need a certain threshold of missing transverse energy, so we need at least 200 GeV. We also need at least 1 jet. The leading jet, or the highest momentum jet, needs to have a transverse momentum of at least 100 GeV. And the delta phi, the minimum delta phi between the jets and our missing transverse energy vector needs to be at least 1. So this is roughly like 60 degrees. You can imagine if there's some error or in the jet momentum reconstruction, that maybe it wouldn't be precisely back to back, even though maybe you'd expect it to be. So that's the reason for this cut. So then what's going into this disappearing track definition?
No.
Sorry, hearing something. Okay, I'll keep going. What's going into this disappearing track definition? There are various straightforward cuts. So for example, there's 4 pixel layers. And if our track goes through, we need to have 4 hits in separate layers. We want our track to point back to the interaction point. So we want it to be within about 1 millimeter of the beam spot. You can imagine if you shift this track around, it wouldn't be pointing back to the beam spot anymore. That would likely be from some kind of background event. This chi-squared probability is noting that since there's a magnetic field in Atlas, we expect our track to have the shape of a helix, and so it should fit that shape. We want that to have a good fit. The overlap removal is we don't want other objects in the event to be nearby, so we don't want any jets or anything else nearby our disappearing track. And then to reduce background from events that scatter off at large angles, we have this calorimeter isolation requirement. So if we look in a cone about our track, we don't want any calorimeter hits in a cone about this track, and that reduces that background. So knowing those cuts, then we want to essentially simulate our model and see if we can obtain some kind of visible cross-section. Luckily, there's various programs that allow us to do this. So we can use this program called Fine Rules. This encodes all the things we would want from our Lagrangian, such as particles, quantum numbers, vertex factors. Then we feed this information into MadGraph, which primarily is calculating the hard scattering process. This is then fed into another program, Pythia, which deals with the showering of hadrons and soft emissions. And finally, we feed this into a program called Delphis, which simulates detector effects. So what we're primarily after is this efficiency, which is reducing what we would ideally see if everything was perfect, I suppose. And that gets reduced down from various detector effects or efficiencies from our selection cuts to some kind of visible cross-section. And then using the background count from the paper, we can obtain our limits. So once we've done those things, one thing to note is that Delphis is good at simulating the calorimeters. So we use this for the jet and missing transverse energy reconstruction. We can't use it for this inner tracker reconstruction. So luckily, Atlas provides a generator level or basically a Pythia level implementation of their search in a program called Simple Analysis. And what this provides for us is an efficiency map for the trigger and for the disappearing track efficiency, parameterized in eta and decay length. So because we have these things, we can effectively obtain our visible cross-section. And then to obtain a significance, we compute the log likelihood ratio, where this mu is multiplying a signal. It's the signal strength. And if we solve for this lambda equals minus 2.71, that corresponds to about a significance of 2 sigma, which is generally what's used for exclusion. So first, we validated our simulation by testing a 3-plit model. This is practically equivalent to the we know. So we should expect to get pretty similar results. And the Atlas search obtains a limit of 660 GeV for the we know, and we luckily obtain a compatible limit of 735 GeV for the 3-plit. And so finally, I'll try to summarize our results. So for the limits for all of our other representations, we have the 5-plit, we get 675 GeV. It's very similar for the 7-plit, and then it seems to drop off for the 9-plit. The reason this is happening is likely because our cross-section scales roughly with dimension squared of our representation, but our mean lifetime is scaling as 1 over n squared minus 1. So what this amounts to is you get some compensation as you go up in dimension from the cross-section, but you're getting punished by the mean lifetime. And so at some point, the tail end of the distribution is getting really small, and so it's likely not making up for that trade-off. So this seems reasonable. So for our projected high luminosity LHC upgrade limits, we assumed they would have 3 inverse attobarms of luminosity. We assume the number of background events were scaled up in proportion with luminosity, although this is somewhat of a conservative thing to do because we assume that there aren't going to be any new analysis techniques or new technology that could be used to remove additional background. So we do see some improvement in the limits here, but notably this is a bit conservative. Okay, so to summarize, looking for these kinds of bottom-up constraints on low energy vacua is a exciting way to constrain the string landscape. There are even models that may constrain the current landscape that exist and are well motivated phenomenologically and are possible to search for with existing technology. And additionally, this line of thinking motivates future collider searches, such as from a muon collider, which would likely greatly improve these bounds on this model. Yeah. Thank you.
Thanks a lot, Rebecca, for your talk. Now I think we have plenty of time for questions. So anyone that has a question about the presentation can ask now. Just unmute yourself or like raise your hand in the Zoom chat. Meanwhile, I think I'm going to ask you a question regarding, so you here, so assume that you have just like a string construction of the standard model, and then you're trying to obtain a higher representation in the SU2. That this problem of like finding higher dimensional representation is like a specific thing of like having the standard model and then the SU2 part, or in general it occurs for like matter representations coming from like string theory constructions.
Yeah, I believe it's just a problem with the high dimension part of it. So it's not really constrained to SU2 exactly. You could think of like SU3 or probably something else. But yeah.
But in any case, you choose SU2 because it could be like the one which would be like easier to measure, or like would have closest like experimental imprint, or it's just an example.
One reason, I guess, is that it is a like simple example, but the other reason is the dark matter motivation. So it is like being searched for with dark matter experiments, and so maybe it's significant that this thing exists that's currently being searched for, but doesn't seem to be a way we can construct it.
Okay, it would be.
Can I ask something? Sorry.
Yeah. Go ahead.
Do you have some similar restriction with the Kac-Moody algebra levels of SU2 or SU3? I don't know if.
Sorry, I'm not quite sure I caught the question.
If like the algebras can appear in different Kac-Moody levels, and the usual thing is to take level 1. I don't know if this affects your computation somehow, or if you need to impose level 1 before restricting the possible representation.
So, I don't know if the 5-foot can be realized if you impose level 1.
Okay.
Or at least the 5-foot, and I would think that at least if you did realize that you would get other things. So the isolation piece of this. For example, if there is a 5-plet, we also want to require that there are no 4-plets or 3-plets that also exist in the spectrum.
Okay, yeah, that's again.
Okay, so do I see another raised hand, or is it like the Munich people? No, Craig Laurie, yeah.
So I'm a little confused about this statement of which representations you can engineer in string theory and which you cannot. So at least if I think about the supersymmetric case, because there at least maybe one can say something. What is the argument that the higher dimensional representations do not appear? If I assume by higher dimensional, I bound myself at sort of asymptotically free. Like, is there a reason that they're expected not to appear, or is the reason just they're harder to construct?
Sorry, I'm trying to think. I'm not quite sure what is changing it with the SUSY argument.
So I'm saying the SUSY argument because if you ask for string constructions of higher fermions in non-SUSY compactifications, then very little is known in general. So I don't know if we can draw conclusions that there does not exist higher dimensional representation since we know so little about non-SUSY compactifications of string theory in the first place. In the SUSY case, maybe we have a chance of knowing more. And there, I don't see an argument that tells you that there are certain representations which do not appear in a string compactification. Right? Other than that, it's hard. But is there an argument? I missed the first 5 or so minutes of the talk, so I may have missed something. But is there some sort of principle which tells you certain things are just not constructible in string theory? Or is it a statement of we've not figured out a way to construct certain things so far?
The statement is that it seems like a strongly motivated conjecture. If I go to like the perturbative open string example, I would guess that maybe because you're requiring maybe the string junction example, because you're requiring the standard model gauge group, it just ends up restricting the kinds of breaking patterns you can realize.
Right. Right. In perturbative type 2b, which I think is already a strong assumption. Like we know that in F theory, you can generate a bunch of stuff that you can't generate in type 2b, like 3 and 4 index antisymmetric or symmetric representations of SU2 and SU3. And these you cannot generate from the type 2b picture.
Yeah, sorry, I'm not sure how to answer.
It's not a good question. I just don't. I'm just trying to understand if there's sort of a principle which tells you that like in string theory in general, these things are just not going to happen, or if the statement is they're sort of hard to construct by the methods we have. And so if we assume the methods we have are the things that construct the real world, then and I think this is what you're saying, like you maybe expect the real world is not some quirky singular divisors in F theory kind of picture, but something more normal. And then you draw conclusions. I think that's maybe what you're telling me. Yeah, sorry, it wasn't a well-formed question. Thank you.
Thanks.
Okay, so I think we can stop with the question part here. There's going to be, in any case, like a discussion at the end, not recorded. So let's just like congratulate again, like clap for Rebecca. Okay.